Picture this: a faint glow, invisible to the naked eye, stretches across the entire universe. It's not just any light, it's the oldest light in existence, a snapshot of the cosmos from over 13 billion years ago. This is the cosmic microwave background, or CMB, and it's not just a relic of the past, it's a cosmic fingerprint, holding secrets from the very dawn of the universe. What if I told you that within this ancient light lie mysteries so profound, they could rewrite everything we think we know about reality? In this video, we're diving into 50 unbelievable mysteries hidden within the CMB. From strange anomalies that defy our understanding of physics to clues about the birth of the universe itself, the CMB is a treasure trove of cosmic secrets waiting to be uncovered. Discovered by accident in the 1960s, this faint afterglow of the Big Bang has become one of the most important tools in cosmology. It's like a time machine, allowing us to peer back to a moment just 380,000 years after the universe began. But what can this ancient light really tell us? Why do scientists consider it one of the most important discoveries in modern science? And what mind-bending mysteries does it hold that could challenge our understanding of the cosmos? From the eerie cold spot anomaly to the puzzling axis of evil, the CMB is full of surprises that keep astronomers and physicists up at night. So, buckle up. We're about to take a journey through time and space, exploring the incredible stories hidden within this cosmic fingerprint. By the end of this video, you'll not only understand why the CMB is so important, you'll also see the universe in a whole new light. Ready to uncover the secrets of the cosmos? Let's begin. Now turning to the first mystery hidden within the cosmic microwave background, we encounter the enigmatic cold spot. Imagine a vast, dark patch in the sky, colder than its surroundings by a significant margin. This is the cold spot, a region in the CMB that has puzzled scientists since its discovery. It's not just a minor fluctuation, it's a glaring anomaly that defies our standard understanding of the universe. The cold spot is so unusual that it challenges the very foundations of cosmology. According to our current models, the universe should be relatively uniform on large scales, with only small, random variations in temperature. But the cold spot is anything but small. It spans an area of the sky about 5 times the size of the full moon, and its temperature is far lower than what we'd expect. This has led to intense debates about its origins. One of the most intriguing theories suggests that the cold spot could be evidence of a collision with another universe. Yes, you heard that right, another universe. In this scenario, our universe might have bumped into a neighboring one during its early expansion, leaving behind a kind of cosmic bruise in the form of the cold spot. While this idea sounds like science fiction, it's a serious hypothesis that some physicists are exploring. Another possibility is that the cold spot is the result of a vast cosmic void, a region of space with far fewer galaxies and matter than usual. If such a void exists, it could distort the light passing through it, creating the illusion of a colder area in the CMB. However, even this explanation raises questions. Why would such a massive void exist, and how could it form in the first place? The cold spot isn't just a curiosity, it's a window into the unknown. If it truly represents a collision with another universe or a cosmic void, it could revolutionize our understanding of the cosmos. It forces us to question whether our current models of the universe are complete or if there's something fundamental we're missing. As we ponder the mysteries of the cold spot, we're reminded that the CMB is more than just a relic of the past. It's a map of the universe's structure. And speaking of maps, our next mystery takes us deeper into how the CMB helps us chart the cosmos, revealing the intricate web of galaxies and clusters that make up our universe. But more on that in a moment. For now, let's marvel at the cold spot, a cosmic enigma that continues to challenge and inspire us. Now turning to the second mystery hidden within the cosmic microwave background, we encounter a phenomenon so peculiar it has been dubbed the axis of evil. This isn't a reference to some cosmic villain, but rather a strange alignment of temperature fluctuations in the CMB that seems to defy one of the most fundamental principles of cosmology, isotropy. Isotropy is the idea that the universe should look the same in all directions, a cornerstone of our understanding of the cosmos. But the axis of evil suggests that this might not be entirely true. The axis of evil refers to a curious pattern in the CMB where certain temperature fluctuations appear to align along a specific axis, almost as if the universe has a preferred direction. This discovery has left scientists scratching their heads. If the universe is truly isotropic, why would there be such a pronounced alignment? It's like finding a compass needle that always points in one direction, no matter where you are in the cosmos. One possible explanation is that this alignment is simply an observational bias, a trick of the data caused by the way we measure the CMB. Perhaps our instruments or methods are inadvertently creating this pattern. However, even after rigorous testing and multiple observations, the axis of evil persists, making it harder to dismiss as a mere artifact. Another possibility is that the axis of evil hints at new physics, something beyond our current understanding of the universe. Some scientists speculate that it could be evidence of a pre-Big Bang structure, a remnant of an earlier phase of the universe that left its mark on the CMB. Others suggest it might be related to the influence of dark energy or even the multiverse, where our universe is just one of many, each with its own unique properties. As physicist Lawrence Krauss once remarked, the axis of evil is a reminder that the universe is far stranger than we can imagine. This mystery challenges us to rethink our assumptions and consider that there may be forces or structures at play that we have yet to uncover. The axis of evil isn't just a scientific curiosity, it's a call to explore the unknown. It reminds us that even the most fundamental principles of cosmology are open to question, and that the universe still holds many secrets waiting to be revealed. As we ponder the implications of this cosmic alignment, we're led to the next mystery, the role of the CMB in understanding dark energy, the mysterious force driving the universe's accelerated expansion. But more on that in a moment. For now, let's reflect on the axis of evil, a cosmic puzzle that continues to challenge our understanding of the universe's structure and origins. Now turning to the third mystery hidden within the cosmic microwave background, we delve into the enigmatic force known as dark energy. This mysterious energy is believed to be the driving force behind the universe's accelerated expansion, a discovery that has fundamentally reshaped our understanding of the cosmos. But how does the CMB help us uncover the secrets of dark energy? The answer lies in the subtle patterns etched into the ancient light of the CMB itself. The CMB's temperature fluctuations act as a cosmic fingerprint, revealing not only the early conditions of the universe but also the distribution of matter and energy over time. By studying these fluctuations, scientists can estimate the amount of dark energy present in the universe. Think of it like this: if the universe were a giant balloon, dark energy would be the invisible hand steadily inflating it, causing galaxies to move farther apart at an ever-increasing rate. The CMB provides a snapshot of this process, allowing us to measure how much dark energy is at work. One of the key ways the CMB helps us understand dark energy is through its role in determining the universe's geometry. The CMB reveals that the universe is flat, meaning parallel lines will never meet. This flatness is a direct consequence of the balance between matter, and dark energy. Without dark energy, the universe's expansion would slow down over time, but observations of the CMB show that the opposite is happening: expansion is speeding up. This acceleration is a hallmark of dark energy's influence. The implications of these findings are profound. If dark energy continues to dominate, the universe will keep expanding faster and faster, eventually leading to a scenario known as the Big Freeze. In this distant future, galaxies will drift so far apart that the night sky will grow darker, and the universe will become a cold, empty expanse. It's a sobering thought, but one that underscores the importance of understanding dark energy and its role in shaping the cosmos. To make this concept more relatable, imagine dark energy as the wind pushing a sailboat across the ocean. At first, the boat moves slowly, but as the wind grows stronger, the boat picks up speed, eventually racing across the water. In the same way, dark energy is propelling the universe's expansion, and the CMB helps us measure just how strong this cosmic wind is. As we reflect on the mysteries of dark energy, we're led to the next puzzle: the role of the CMB in understanding dark matter, the invisible substance that makes up most of the universe's mass. But more on that in a moment. For now, let's marvel at how the CMB serves as a cosmic detective, uncovering clues about the forces that shape our universe's past, present, and future. Now turning to the fourth mystery hidden within the cosmic microwave background, we uncover the shadowy presence of dark matter, the invisible substance that makes up most of the universe's mass. While dark matter doesn't emit, absorb, or reflect light, its gravitational influence is undeniable, shaping the cosmos in ways we can observe through the CMB. But how does this ancient light help us detect something so elusive? The answer lies in a phenomenon called gravitational lensing. Gravitational lensing occurs when massive objects like galaxies or clusters of galaxies bend the path of light traveling through space. This bending acts like a cosmic magnifying glass, distorting the images of objects behind it. In the case of the CMB, dark matter's gravitational pull subtly warps the ancient light, creating tiny distortions in its temperature patterns. By analyzing these distortions, scientists can map the distribution of dark matter across the universe. It's like using the CMB as a cosmic canvas, where the brushstrokes of dark matter reveal themselves through the warped light. One of the most remarkable breakthroughs enabled by CMB observations is the ability to trace the large-scale structure of the universe. Dark matter acts as the scaffolding upon which galaxies and galaxy clusters form, and the CMB provides a snapshot of this cosmic framework. Without dark matter, the universe as we know it wouldn't exist. Its gravitational pull is what allowed matter to clump together and form the first stars and galaxies. Yet, despite its critical role, dark matter remains one of the greatest mysteries in modern science. Studying something that doesn't interact with light poses significant challenges. Unlike stars or gas clouds, dark matter can't be observed directly. Instead, we rely on its gravitational effects to infer its presence. The CMB has become an invaluable tool in this quest, offering a window into the early universe where dark matter's influence is imprinted on the ancient light. These observations have allowed scientists to estimate that dark matter makes up about 27% of the universe's total mass energy content, far outweighing the 5% contributed by ordinary matter. To put this into perspective, imagine the universe as a vast ocean. Ordinary matter is like the visible waves on the surface, while dark matter is the deep, unseen current beneath, guiding the motion of everything above. The CMB helps us measure these hidden currents, revealing the invisible forces that shape the cosmos. As we marvel at the breakthroughs enabled by the CMB, we're led to the next mystery: the CMB's connection to the Big Bang itself. How does this ancient light serve as a time capsule, offering a glimpse into the universe's fiery birth? But more on that in a moment. For now, let's appreciate how the CMB continues to illuminate the shadows of the cosmos, uncovering the secrets of dark matter and its profound influence on the universe's structure. Now turning to the fifth mystery hidden within the cosmic microwave background, we encounter what is often called the afterglow of the Big Bang. This ancient light, the CMB, is a snapshot of the universe as it was just 380,000 years after its explosive birth. At that time, the universe was a seething, opaque plasma, too hot and dense for light to travel freely. But as it expanded and cooled, electrons and protons combined to form the first atoms, allowing light to break free and travel across the cosmos. This moment, known as the Era of Recombination, marked the birth of the CMB, a faint glow that has been traveling through space for over 13 billion years, carrying with it the secrets of the universe's infancy. The CMB is more than just a relic of the past. It's a cosmic time capsule, preserving the conditions of the early universe in exquisite detail. By studying its temperature fluctuations, scientists can peer back in time to an era when the universe was 1,000 times smaller and 1,000,000 times hotter than it is today. These fluctuations, tiny variations in temperature across the sky, are like fingerprints left by the primordial universe. They reveal the seeds of structure, the slight overdensities and underdensities in matter that would eventually grow into galaxies, clusters, and the vast cosmic web we see today. What makes the CMB so extraordinary is its ability to test our theories about the universe's origins. For instance, the Big Bang theory predicts that the early universe should have been filled with a nearly uniform glow of radiation, and the CMB matches this prediction with stunning precision. But it also holds surprises. The precise measurements of the CMB's temperature fluctuations have allowed scientists to refine their understanding of the universe's composition, age, and expansion rate. It's like having a detailed map of the universe's first moments, one that confirms some of our boldest ideas while challenging others. The awe-inspiring nature of this discovery lies in its simplicity. The CMB is a faint whisper from the dawn of time, a signal so subtle that it was only discovered by accident in 1965. Yet, it has become one of the most powerful tools in cosmology, offering a direct link to the universe's fiery beginnings. It's a reminder that even the faintest echoes can carry profound truths, and that the universe's oldest light still has much to teach us. As we marvel at the CMB's role as a cosmic time capsule, we're led to the next mystery, its connection to cosmic inflation. How does this ancient light provide evidence for the universe's rapid expansion in its earliest moments? But more on that in a moment. For now, let's appreciate how the CMB continues to illuminate the universe's origins, offering a glimpse into the very first chapter of cosmic history. Now turning to the sixth mystery hidden within the cosmic microwave background, we delve into one of the most profound ideas in modern cosmology, cosmic inflation. This theory proposes that in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, growing from a subatomic speck to something far larger in an unimaginably short time. But how does the CMB, a relic from hundreds of thousands of years later, provide evidence for this rapid expansion? The answer lies in the tiny temperature fluctuations scattered across the CMB's map of the sky. These fluctuations, often described as the universe's first whispers, are not random. Instead, they follow a specific pattern that aligns remarkably well with the predictions of cosmic inflation. According to the theory, quantum fluctuations in the early universe were stretched to cosmic scales during inflation, creating the slight variations in density that would later become the seeds for galaxies and galaxy clusters. The CMB captures these fluctuations as minute differences in temperature, with some regions slightly warmer or cooler than the average. These variations are incredibly small, on the order of 1 part in 100,000, but they are precisely what inflation models predict. What makes this evidence so compelling is its consistency. The CMB's temperature fluctuations match the theoretical predictions of inflation with astonishing precision. For example, inflation predicts that these fluctuations should be nearly scale invariant, meaning they should look similar whether you zoom in or out on the cosmic map. And that's exactly what we see in the CMB. This alignment between theory and observation has made cosmic inflation one of the most widely accepted ideas in cosmology, offering a powerful explanation for the universe's large-scale structure. But the implications of this evidence go even deeper. If inflation did occur, it would explain why the universe appears so uniform on large scales. The rapid expansion would have smoothed out any irregularities, creating the nearly homogeneous cosmos we observe today. It would also provide a mechanism for generating the tiny quantum fluctuations that eventually grew into the galaxies, stars, and planets we see around us. In this way, the CMB doesn't just confirm inflation, it connects the dots between the universe's earliest moments and its present-day structure. The discovery of these temperature fluctuations has reshaped our understanding of the universe's birth, but it also raises new questions. For instance, what triggered inflation in the first place, and what lies beyond the observable universe in regions that inflation pushed far beyond our cosmic horizon? These questions hint at even grander mysteries, some of which may be tied to the idea of a multiverse, a vast collection of universes, each with its own unique properties. But more on that in a moment. For now, let's marvel at how the CMB has illuminated the universe's explosive beginnings, offering a glimpse into the fleeting moments when everything we know came into being. Now turning to the seventh mystery hidden within the cosmic microwave background, we venture into one of the most mind-bending ideas in modern physics, the Multiverse Hypothesis. Could the CMB, this ancient light from the dawn of the universe, hold clues about the existence of other universes beyond our own? Some scientists believe it might, and the evidence lies in the strange anomalies we've already encountered, like the cold spot and the axis of evil. The cold spot, as we've discussed, is a region in the CMB that's significantly colder than its surroundings. While some explanations point to cosmic voids or other natural phenomena, others have proposed a far more radical idea, that the cold spot could be the imprint of a collision with another universe. Imagine for a moment that our universe is just one bubble in a vast cosmic foam, with other universes floating nearby. If two of these bubbles collided, the energy released could leave a mark on the CMB, a mark like the cold spot. While this idea is still speculative, it's a tantalizing possibility that challenges our understanding of reality. Then there's the axis of evil, the peculiar alignment of temperature fluctuations in the CMB that seems to defy the principle of isotropy, the idea that the universe should look the same in all directions. Some researchers have suggested that this alignment could be evidence of a larger structure beyond our universe, perhaps a neighboring universe exerting a gravitational influence on ours. If true, this would mean that the CMB is not just a map of our universe but a window into a much larger multiverse. These anomalies have sparked intense debate among scientists. Could we be living in just one of countless universes, each with its own unique laws of physics? The idea of a multiverse is both thrilling and humbling, suggesting that our universe might be just one small part of an unimaginably vast cosmic landscape. But how could we ever prove such a thing? The CMB might hold the key. By studying its anomalies in greater detail, we could uncover evidence of interactions with other universes, offering a glimpse into realities beyond our own. The multiverse hypothesis raises profound questions about the nature of existence. What would other universes look like? Could they have different physical constants, or even entirely different forms of matter and energy? And if they exist, what does that mean for our place in the cosmos? While these questions remain unanswered, the CMB continues to be a powerful tool for exploring the boundaries of our understanding. As we ponder these possibilities, let's not forget that the CMB also holds clues about the age of our universe. How old is the cosmos, and how do we know? That's the mystery we'll explore next as we continue our journey through the incredible secrets hidden in the cosmic microwave background. Now turning to the eighth mystery hidden within the cosmic microwave background, we delve into one of the most fundamental questions in cosmology: how old is the universe? The CMB, this ancient light from the dawn of time, provides one of the most precise answers we have. According to current estimates, the universe is approximately 13.8 billion years old. But how do scientists arrive at this number, and why is it so important? To understand how the CMB helps us measure the universe's age, let's start with the basics. The CMB is essentially a snapshot of the universe when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This light has been traveling through space ever since, carrying with it a wealth of information about the early universe. By studying the CMB's temperature fluctuations and the patterns they form, scientists can piece together the history of the cosmos. One of the key methods used to calculate the universe's age involves measuring the rate at which the universe is expanding. This expansion rate, known as the Hubble constant, tells us how fast galaxies are moving away from each other. By combining this information with the CMB's data, scientists can work backward to determine when the universe began. Think of it like rewinding a movie. If you know how fast the scenes are playing, you can figure out when the movie started. The CMB also provides clues about the universe's composition, including the amounts of ordinary matter, dark matter, and dark energy. These ingredients play a crucial role in shaping the universe's expansion and, by extension, its age. For example, dark energy, the mysterious force driving the universe's accelerated expansion, affects how quickly the universe grows over time. By factoring in these elements, scientists can refine their calculations and arrive at the precise age of 13.8 billion years. This measurement is more than just a number, it's a cornerstone of modern cosmology. It helps us understand the timeline of cosmic events, from the formation of the first atoms to the birth of galaxies and stars. It also provides a framework for testing theories about the universe's origins and evolution. Without the CMB, we wouldn't have such a clear picture of how old the universe is or how it has changed over time. To put this into perspective, imagine the universe's age as a book with 13.8 billion pages. Each page represents 1 year of cosmic history. The CMB gives us a glimpse of the very first chapter, allowing us to piece together the story that follows. It's a story of expansion, transformation, and the emergence of complexity, all written in the language of light. As we marvel at the precision of this measurement, let's not forget that the CMB also holds clues about the universe's shape. Is the cosmos flat, curved, or something else entirely? That's the mystery we'll explore next as we continue our journey through the incredible secrets hidden in the cosmic microwave background. Now turning to the 9th mystery hidden within the cosmic microwave background, we explore one of the most profound revelations about the universe, its geometry. The CMB has provided compelling evidence that the universe is flat, meaning that parallel lines will never meet, no matter how far they travel through space. This discovery is not just a fascinating piece of cosmic trivia, it has profound implications for our understanding of the universe's origins, evolution, and ultimate fate. To grasp why the universe's flat geometry is so significant, let's start with the basics. In geometry, flatness refers to a space where the rules of Euclidean geometry apply. In a flat universe, the angles of a triangle add up to 180 degrees, and parallel lines remain parallel forever. This might sound straightforward, but it's a critical clue about the universe's overall structure. The CMB's temperature fluctuations, which we've discussed earlier, provide a cosmic map that allows scientists to measure the curvature of space. And what they've found is that, on the largest scales, the universe appears to be flat. This finding aligns perfectly with the predictions of cosmic inflation, the theory that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. Inflation would have stretched the fabric of space so dramatically that any initial curvature would have been smoothed out, leaving the universe flat. The CMB's flatness is one of the strongest pieces of evidence supporting this theory, helping to confirm that inflation likely occurred. But what does a flat universe mean for its ultimate fate? The geometry of the universe is closely tied to its density. In a flat universe, the total amount of matter and energy is precisely balanced, meaning the universe will continue to expand forever, though at an ever-slowing rate. This stands in contrast to a closed universe which would eventually collapse in on itself, or an open universe which would expand indefinitely at an accelerating pace. The CMB's evidence for flatness suggests that our universe is destined for a slow, steady expansion, with galaxies drifting apart over trillions of years. This discovery also has implications for the nature of dark energy, the mysterious force driving the universe's accelerated expansion. A flat universe requires a specific amount of dark energy to maintain its geometry, and the CMB's measurements help scientists refine their understanding of this enigmatic component. Without the CMB, we wouldn't have such a clear picture of how the universe's geometry, expansion, and composition are interconnected. As we marvel at the implications of a flat universe, let's not forget that the CMB also holds clues about another cosmic puzzle, the Hubble constant. This key parameter, which describes the rate at which the universe is expanding, has sparked one of the biggest debates in modern cosmology. That's the mystery we'll explore next as we continue our journey through the incredible secrets hidden in the cosmic microwave background. Now turning to the 10th mystery hidden within the cosmic microwave background, we delve into one of the most perplexing challenges in modern cosmology, the Hubble tension. The Hubble constant, a critical parameter that describes the rate at which the universe is expanding, has become the center of a heated debate among scientists. Measurements of the CMB have revealed a discrepancy in the value of this constant, creating what is known as the Hubble tension, a puzzle that could reshape our understanding of the cosmos. To understand the significance of this tension, let's start with the basics. The Hubble constant is named after Edwin Hubble, the astronomer who first discovered that the universe is expanding. It quantifies how fast galaxies are moving away from us, with the rate increasing as their distance from us grows. For decades, scientists have worked to measure this constant with precision using two primary methods. The first involves observing distant supernovae and other cosmic objects to calculate the expansion rate directly. The second relies on the CMB, which provides a snapshot of the early universe and allows scientists to infer the Hubble constant based on the universe's initial conditions. Here's where the tension arises. Measurements from the CMB, such as those made by the Planck satellite, suggest a Hubble constant of around 67 kilometers per second per megaparsec. However, observations of nearby supernova and other local objects yield a higher value, closer to 73 kilometers per second per megaparsec. This discrepancy might seem small, but in the precise world of cosmology, it's a glaring inconsistency that has left scientists scratching their heads. Why does this matter? The Hubble constant is a cornerstone of our understanding of the universe's evolution. If the value derived from the CMB is correct, it implies that our models of the early universe are accurate, but our understanding of its current state might be incomplete. On the other hand, if the local measurements are correct, it could mean that there's something missing in our theories about the universe's early moments. Some scientists have even speculated that this tension could hint at new physics, such as an unknown form of dark energy or modifications to Einstein's theory of gravity. As Nobel laureate Adam Rees, a leading figure in this debate, once said, "The Hubble tension is not just a measurement problem, it's a clue that we might be missing something fundamental about the universe." This ongoing debate highlights the importance of the CMB as a tool for probing the cosmos. Its ability to reveal inconsistencies in our understanding of the universe's expansion rate underscores its role as a cosmic detective, uncovering mysteries that challenge our most fundamental assumptions. As we grapple with the implications of the Hubble tension, let's not forget that the CMB also holds clues about another cosmic puzzle, the universe's composition. That's the mystery we'll explore next as we continue our journey through the incredible secrets hidden in the cosmic microwave background. Now turning to the 11th mystery hidden within the cosmic microwave background, we explore the universe's recipe, a precise breakdown of its ingredients that has reshaped our understanding of cosmic evolution. Just as a chef relies on a recipe to create a dish, scientists use the CMB to uncover the exact proportions of ordinary matter, dark matter, and dark energy that make up the cosmos. This cosmic recipe not only tells us what the universe is made of, but also how these components have shaped its history and will determine its future. The CMB acts as a cosmic time capsule, preserving the conditions of the universe just 380,000 years after the Big Bang. By analyzing the tiny temperature fluctuations in this ancient light, scientists can calculate the amounts of ordinary matter, dark matter, and dark energy with remarkable precision. Ordinary matter, the stuff that makes up stars, planets, and everything we can see, accounts for only about 5% of the universe's total content. Dark matter, an invisible substance that exerts gravitational pull but doesn't emit light, makes up roughly 27%. The remaining 68% is dark energy, the mysterious force driving the universe's accelerated expansion. These proportions might seem abstract, but they have profound implications for our understanding of the cosmos. Ordinary matter, though a small fraction, is the building block of galaxies, stars, and life itself. Without it, the universe would be a dark, empty void. Dark matter, on the other hand, acts as the cosmic scaffolding, holding galaxies together and shaping the large-scale structure of the universe. Without its gravitational influence, galaxies would fly apart, and the universe as we know it wouldn't exist. Dark energy, the most enigmatic of the three, is responsible for the universe's accelerating expansion. Its presence suggests that the cosmos is not only growing but doing so at an ever-increasing rate, leading to a future where galaxies may drift so far apart that they become invisible to one another. The discovery of this cosmic recipe has revolutionized cosmology. It has allowed scientists to test and refine theories about the universe's origins, evolution, and ultimate fate. For example, the precise measurements of dark energy from the CMB have confirmed that it dominates the universe's energy budget, a finding that has profound implications for the cosmos's long-term destiny. Similarly, the balance between dark matter and ordinary matter has helped explain why galaxies form in the way they do and why the universe looks the way it does today. As we marvel at the universe's recipe, it's worth noting that the CMB also holds clues about how these ingredients came together to form the cosmic structures we see today. That's the mystery we'll explore next as we delve into the CMB's role in understanding the seeds of cosmic structures, the tiny fluctuations that grew into galaxies, clusters, and the vast web of the universe. Now turning to the 12th mystery hidden within the cosmic microwave background, we uncover the seeds of cosmic structures, the tiny fluctuations that set the stage for the formation of galaxies, clusters, and the vast web of the universe. Imagine these fluctuations as the faint ripples on the surface of a pond, barely visible at first but destined to grow into waves that shape the entire landscape. In the same way, the minuscule variations in temperature and density preserved in the CMB acted as the initial seeds for the universe's grand architecture. These fluctuations, though incredibly small, just 1 part in 100,000, were enough to set the universe on a path of transformation. Over billions of years, gravity took hold of these tiny irregularities, amplifying them and drawing matter together. Denser regions attracted more matter, growing into the first clumps of gas and dust. These clumps eventually collapsed under their own gravity, igniting the first stars and forming the earliest galaxies. Meanwhile, the less dense regions became the vast cosmic voids we see today, creating a tapestry of light and shadow that defines the universe's large-scale structure. To put this into perspective, think of the universe as a loaf of bread rising in the oven. The tiny air bubbles in the dough are like the initial fluctuations in the CMB. As the bread bakes, these bubbles expand and merge, creating larger pockets of air that give the loaf its final texture. Similarly, the universe's fluctuations grew and interconnected, forming the intricate web of galaxies and clusters we observe today. This process, driven by gravity and the interplay of dark matter and ordinary matter, took billions of years to unfold, but its origins can be traced back to those first faint imprints in the CMB. The CMB's role in revealing these seeds is nothing short of extraordinary. By mapping the temperature variations in this ancient light, scientists can reconstruct the early universe's conditions and trace how these fluctuations evolved over time. This has allowed them to test theories about the formation of cosmic structures and refine our understanding of the universe's growth. For instance, the distribution of galaxies and clusters we see today matches the predictions made by analyzing the CMB, providing strong evidence for our current cosmological models. As we marvel at how these tiny seeds grew into the universe's vast structures, it's worth considering what the CMB can tell us about the conditions that allowed this growth to begin. That's the mystery we'll explore next as we delve into the CMB's role in understanding the early universe's temperature, a key factor that shaped the cosmos's evolution from its fiery beginnings to the intricate web we see today. Now turning to the 13th mystery hidden within the cosmic microwave background, we explore the early universe's temperature, a critical piece of the puzzle that helps us understand how the cosmos evolved from its fiery beginnings. The CMB provides us with a precise snapshot of the universe's temperature just 380,000 years after the Big Bang, a time when the cosmos was a seething cauldron of energy and matter. This temperature, measured at around 2,700 Kelvin, or roughly 4,900 degrees Fahrenheit, offers a window into the extreme conditions that shaped the universe's infancy. To grasp the significance of this temperature, imagine the early universe as a dense, scorching plasma, a chaotic soup of particles and radiation. At such high temperatures, atoms couldn't form because the intense heat ripped electrons away from protons, creating a state of matter where light couldn't travel freely. The universe was opaque, a glowing fog of energy that trapped photons in a constant dance of scattering and absorption. This extreme heat was not just a byproduct of the Big Bang. It was the driving force behind the universe's early evolution, dictating how matter and energy interacted and setting the stage for the formation of the first structures. The CMB's measurement of this temperature is like a cosmic thermometer, allowing scientists to reconstruct the conditions of the early universe with remarkable precision. By studying the CMB, researchers can determine how the universe cooled over time, transitioning from a blazing inferno to a more hospitable environment where atoms could finally form. This cooling process was essential for the universe's transformation, as it allowed matter to clump together and gravity to take hold, eventually leading to the birth of stars, galaxies, and the intricate cosmic web we see today. The extreme heat of the early universe also played a crucial role in shaping the distribution of matter and energy. The intense radiation pressure from the hot plasma smoothed out irregularities, creating the nearly uniform conditions we observe in the CMB. However, the tiny fluctuations in temperature, those seeds of cosmic structures we discussed earlier, were preserved, providing the blueprint for the universe's large-scale structure. Without the precise measurement of the early universe's temperature, we wouldn't be able to understand how these fluctuations evolved or how the cosmos transitioned from a uniform sea of energy to the diverse and dynamic universe we inhabit today. As we reflect on the early universe's temperature and its role in shaping the cosmos, it's worth considering what happened next. How did the universe cool enough for atoms to form? And what does this tell us about the era of recombination? That's the mystery we'll explore next as we delve into the CMB's connection to the universe's first atoms, a pivotal moment that marked the dawn of light and the birth of the cosmos as we know it. Now turning to the 14th mystery hidden within the cosmic microwave background, we explore the Era of Recombination, a pivotal moment in the universe's history when the cosmos cooled enough for electrons and protons to combine, forming the first atoms. This era, occurring roughly 380,000 years after the Big Bang, marked a dramatic shift in the universe's evolution, transforming it from an opaque, glowing plasma into a transparent gas where light could finally travel freely. The CMB we observe today is the direct result of this transformation, a snapshot of the universe's first light breaking free from the fog of its fiery beginnings. To understand the significance of this era, imagine the early universe as a dense, chaotic soup of particles and radiation. For hundreds of thousands of years, the universe was so hot that electrons and protons couldn't stay together. Every time they tried to form an atom, the intense heat ripped them apart, creating a state of matter where light was constantly scattered and absorbed. The universe was like a thick, glowing fog, trapping photons in a relentless dance of collision and re-emission. But as the universe expanded and cooled, the temperature dropped to a point where electrons and protons could finally combine to form neutral hydrogen atoms. This moment, known as recombination, was a cosmic turning point. The Era of Recombination was like the universe taking its first breath of clarity. As atoms formed, the fog of plasma cleared and light was no longer trapped. Photons could now travel freely through space, creating the first light that would eventually become the CMB we observe today. This light, emitted during recombination, carries with it a wealth of information about the early universe, from its temperature and density to the tiny fluctuations that would later grow into galaxies and cosmic structures. The significance of this era cannot be overstated. Without recombination, the universe would have remained opaque, and we would have no way of observing its early history. The CMB is essentially a time capsule, preserving the conditions of the universe at the moment light broke free. By studying the CMB, scientists can reconstruct the universe's state during recombination, gaining insights into how matter and energy evolved in the cosmos's infancy. As we reflect on the Era of Recombination, it's worth considering what happened next. How did this first light shape the universe, and what does it tell us about the cosmos's earliest moments? That's the mystery we'll explore next, as we delve into the CMB's connection to the universe's first light, a journey that will take us even closer to understanding the dawn of the cosmos as we know it. Now turning to the 15th mystery hidden within the cosmic microwave background, we explore the universe's first light, a profound moment when the cosmos transitioned from an opaque, glowing plasma to a transparent gas, allowing light to travel freely for the first time. This light, captured in the CMB, is not just a relic of the past, it's a beacon illuminating the universe's earliest history, offering us a glimpse into the dawn of creation. Imagine the universe as a newborn, emerging from the chaos of its fiery beginnings. For hundreds of thousands of years, it was shrouded in a dense fog of particles and radiation, trapping light in a constant cycle of scattering and absorption. But as the universe expanded and cooled, it reached a critical moment, the Era of Recombination. Here, electrons and protons combined to form the first atoms, and the cosmic fog lifted. Light, once imprisoned, was finally set free. This first light, emitted during recombination, is what we now observe as the CMB. It's the oldest light in the universe, a snapshot of the cosmos just 380,000 years after the Big Bang. The significance of this first light cannot be overstated. It carries with it the fingerprints of the early universe, encoding information about its temperature, density, and the tiny fluctuations that would later grow into galaxies, stars, and planets. By studying the CMB, scientists can reconstruct the conditions of the universe at this pivotal moment, piecing together the story of how matter and energy evolved in the cosmos's infancy. It's like having a time machine that takes us back to the universe's first breath of clarity. This first light is also a testament to the universe's resilience and creativity. From a hot, dense plasma to a transparent gas teeming with the potential for structure and life, the universe underwent a transformation that set the stage for everything we see today. The CMB is not just a relic, it's a roadmap guiding us through the universe's earliest chapters and helping us understand how the cosmos grew from a simple, uniform state into the complex, beautiful tapestry we observe today. As we marvel at the universe's first light, it's worth considering what happened next. How did this light interact with the cosmos, and what role did it play in shaping the universe's evolution? That's the mystery we'll explore next as we delve into the CMB's connection to the universe's first sound waves, a journey that will take us even deeper into the cosmic symphony that began with the Big Bang. Now turning to the 16th mystery hidden within the cosmic microwave background, we uncover the echoes of the universe's first sound waves, ripples that traveled through the early cosmos like the notes of a cosmic symphony. These sound waves, known as baryon acoustic oscillations, are not just remnants of the universe's infancy. They are a powerful tool that helps scientists measure the vast distances of space and time. Imagine the early universe as a dense, hot soup of particles and radiation. In this chaotic environment, pressure waves began to ripple outward, much like the sound waves created by a clap of thunder. These waves were driven by the interplay between gravity, which pulled matter together, and radiation pressure, which pushed it apart. As the universe expanded and cooled, these ripples froze into the fabric of space, leaving behind a pattern of peaks and troughs in the distribution of matter. This pattern is imprinted in the CMB like a fossilized record of the universe's first vibrations. These baryon acoustic oscillations serve as a cosmic ruler, allowing scientists to measure distances across the universe with remarkable precision. By studying the spacing between the peaks in the CMB, researchers can determine how far apart galaxies and other cosmic structures are today. This information is crucial for understanding the rate at which the universe is expanding and for testing theories about dark energy, the mysterious force driving this acceleration. It's like having a yardstick that stretches across billions of light years, helping us map the cosmos with unprecedented accuracy. The significance of these sound waves goes beyond measurement. They provide a window into the universe's evolution, revealing how tiny fluctuations in density grew over billions of years to form the galaxies, clusters, and filaments we see today. The CMB captures the moment when these fluctuations were still in their infancy, offering a snapshot of the seeds from which the universe's large-scale structure would eventually sprout. By studying these patterns, scientists can trace the history of cosmic growth, from the first ripples of sound to the intricate web of galaxies that spans the cosmos today. As we listen to the echoes of these ancient sound waves, it's worth reflecting on the universe's remarkable ability to transform chaos into order. From the first vibrations of the early cosmos to the vast structures that fill the sky, the universe has been shaped by forces both subtle and profound. And as we continue our journey through the mysteries of the CMB, we'll explore how these sound waves connect to the formation of the universe's first elements, a story that takes us even deeper into the origins of everything we know. Now turning to the 17th mystery hidden within the cosmic microwave background, we delve into the story of the universe's first elements, hydrogen and helium. These simple yet fundamental building blocks of the cosmos were forged in the fiery crucible of the early universe, and the CMB holds the key to understanding how they came to be. This process, known as nucleosynthesis, is one of the most critical chapters in the history of the universe, and it all began just minutes after the Big Bang. Picture the universe in its earliest moments, a seething cauldron of energy and particles. As the cosmos expanded and cooled, conditions became just right for the first atomic nuclei to form. During this brief window, protons and neutrons combined to create the nuclei of hydrogen and helium, the lightest and most abundant elements in the universe. This process, called Big Bang nucleosynthesis, was like a cosmic recipe, with the universe's temperature and density acting as the perfect ingredients to cook up these elements. By the time the universe was just a few minutes old, nearly all the hydrogen and helium we see today had already been created. The CMB provides a snapshot of this moment, capturing the aftermath of nucleosynthesis. The temperature fluctuations in the CMB reflect the distribution of matter and energy at the time, including the newly formed hydrogen and helium. By studying these patterns, scientists can determine the exact proportions of these elements and compare them to predictions made by theoretical models. This alignment between observation and theory is one of the strongest pieces of evidence supporting the Big Bang model, confirming that the universe's first elements were indeed forged in its fiery beginnings. But why are hydrogen and helium so important? These elements are the raw materials from which everything else in the universe is made. Hydrogen, the simplest element, consists of just one proton and one electron, while helium, the next lightest, has 2 protons, 2 neutrons, and 2 electrons. Together, they make up more than 98% of the ordinary matter in the universe. Without these elements, stars could not form, galaxies could not exist, and life as we know it would be impossible. In a sense, the story of the universe is the story of how hydrogen and helium gave rise to everything else. The process of nucleosynthesis didn't stop with the Big Bang. Later, inside the cores of stars, heavier elements like carbon, oxygen, and iron were created through nuclear fusion. But it all started with hydrogen and helium, the seeds of cosmic evolution. The CMB allows us to peer back in time and witness the moment when these seeds were planted, offering a glimpse into the universe's earliest moments. As we reflect on the formation of the universe's first elements, it's remarkable to think that the same hydrogen and helium that filled the early cosmos now flow through our veins, power the stars, and shape the galaxies. The CMB not only tells us where we came from, but also connects us to the vast tapestry of the cosmos. And as we continue our journey through the mysteries of the CMB, we'll explore how these elements connect to another cosmic enigma: the universe's first magnetic fields, a force that may have shaped the cosmos in ways we are only beginning to understand. Now turning to the 18th mystery hidden within the cosmic microwave background, we explore the enigmatic possibility of primordial magnetic fields. These ancient magnetic fields, if they exist, could hold the key to understanding some of the universe's earliest moments. But what exactly are primordial magnetic fields, and why are they so difficult to detect? Let's dive into this cosmic puzzle. Primordial magnetic fields are thought to have formed in the very early universe, potentially even before the first stars and galaxies came into existence. Unlike the magnetic fields we observe today, which are generated by stars, planets, and galaxies, these fields would have been present on a much larger scale, woven into the fabric of space itself. The idea is that these fields could have influenced the formation of cosmic structures, shaping the way matter clumped together to form galaxies and clusters. But detecting these ancient magnetic fields is no easy task. The CMB, which is essentially a snapshot of the universe when it was just 380,000 years old, might hold subtle clues. Tiny distortions in the CMB's polarization, the orientation of its light waves, could hint at the presence of these fields. However, these signals are incredibly faint, buried beneath layers of cosmic noise. Scientists are using advanced instruments and sophisticated algorithms to sift through the data, searching for the telltale signs of primordial magnetism. Why does this matter? If primordial magnetic fields are discovered, they could revolutionize our understanding of cosmic evolution. For one, they might explain how the first galaxies formed so quickly after the Big Bang. These fields could have acted as cosmic scaffolding, guiding the flow of matter and accelerating the growth of structures. They might also shed light on the nature of dark matter and dark energy, two of the greatest mysteries in modern cosmology. Could these fields have interacted with dark matter in ways we've yet to imagine? Or might they have influenced the expansion of the universe itself? The search for primordial magnetic fields is a reminder of how much we still have to learn about the cosmos. It's a journey that takes us back to the very beginning, to a time when the universe was a blank canvas waiting to be painted with the first strokes of creation. And as we continue to probe the CMB for answers, we're not just uncovering the secrets of the past, we're also gaining insights into the forces that shape our universe today. With this mystery still unfolding, we now turn our attention to another cosmic enigma, the universe's first black holes. These mysterious objects born in the early universe may hold clues to the formation of galaxies and the evolution of the cosmos itself. What role did they play in shaping the universe we see today? Let's explore this next chapter in our journey through the mysteries of the CMB. Now turning to the 19th mystery hidden within the cosmic microwave background, we delve into the enigmatic origins of the universe's first black holes. These ancient cosmic giants born in the fiery chaos of the early universe may hold the key to understanding how galaxies formed and evolved. But how can the CMB, a faint echo of the universe's infancy, shed light on these mysterious objects? Let's explore this cosmic puzzle. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. The first black holes, often referred to as primordial black holes, are thought to have formed in the earliest moments of the universe, long before the first stars and galaxies came into existence. Unlike the black holes we observe today, which are born from the collapse of massive stars, these primordial black holes could have formed directly from the extreme density fluctuations in the young universe. The CMB, with its intricate patterns of temperature and polarization, might carry subtle imprints of these ancient objects. One of the biggest challenges in studying the first black holes is their elusive nature. They are incredibly difficult to detect directly, especially if they are small or have since merged into larger structures. However, the CMB offers a unique window into their existence. For instance, if primordial black holes were abundant in the early universe, their gravitational influence could have left subtle distortions in the CMB's temperature fluctuations. These distortions, though incredibly faint, could be detected with precise measurements and advanced data analysis techniques. Another intriguing possibility is that these early black holes played a crucial role in seeding the formation of galaxies. As they grew and merged, their immense gravitational pull could have drawn in surrounding matter, creating the dense regions that eventually collapsed into the first stars and galaxies. This process might explain why some galaxies formed so quickly after the Big Bang, a phenomenon that has puzzled scientists for decades. The CMB could help us test this idea by revealing how matter was distributed in the early universe and whether black holes were the cosmic architects behind these structures. The study of primordial black holes also has profound implications for our understanding of dark matter. Some theories suggest that these ancient black holes could account for a portion of the universe's dark matter, the invisible substance that makes up most of its mass. If true, this would revolutionize our understanding of both black holes and dark matter, two of the most mysterious components of the cosmos. As we continue to probe the CMB for clues about the first black holes, we are reminded of the universe's endless capacity to surprise us. These ancient objects, born in the chaos of the early universe, may hold the answers to some of our deepest questions about cosmic evolution. And as we uncover their secrets, we move closer to understanding the forces that shape the universe we see today. With this mystery still unfolding, we now turn our attention to another cosmic enigma, the universe's first stars. These ancient beacons, born from the ashes of the Big Bang, lit up the cosmos and set the stage for the formation of galaxies. What role did they play in shaping the universe? Let's explore this next chapter in our journey through the mysteries of the CMB. Now turning to the 20th mystery hidden within the cosmic microwave background, we step into the era of the first stars, a time often referred to as the cosmic dawn. This pivotal period marks the moment when the universe transitioned from a dark, featureless expanse to a luminous tapestry of light and structure. But how does the CMB, a relic of the universe's infancy, help us understand these ancient beacons of light? Let's uncover the story of the first stars and their profound impact on the cosmos. The cosmic dawn began roughly 100 million years after the Big Bang, when the universe had cooled enough for the first atoms to form. These atoms, primarily hydrogen and helium, began to clump together under the force of gravity, creating dense clouds that eventually ignited into the first stars. These stars were unlike any we see today, massive, hot, and short-lived. They burned brightly and died young, seeding the universe with heavier elements like carbon, oxygen, and nitrogen. The CMB provides a unique window into this era by capturing the faint echoes of the light these stars emitted and the changes they brought to the universe. One of the most fascinating ways the CMB helps us study the first stars is through its polarization patterns. As the first stars lit up, their intense ultraviolet radiation ionized the surrounding hydrogen gas, a process known as reionization. This event left a distinct imprint on the CMB's polarization, allowing scientists to map when and how quickly reionization occurred. By analyzing these patterns, researchers can piece together the timeline of the cosmic dawn and understand how the first stars transformed the universe from a dark, neutral state to one filled with light and ionized gas. The first stars also played a crucial role in shaping the large-scale structure of the universe. As they formed and died, they released energy and heavy elements into their surroundings, enriching the cosmic environment and paving the way for the formation of future stars and galaxies. Without these early stars, the universe as we know it, filled with galaxies, planets, and life, would not exist. The CMB helps us trace this cosmic evolution by revealing how the distribution of matter and energy changed over time, offering clues about the conditions that allowed the first stars to form. To put it simply, the first stars were like the pioneers of the cosmos, lighting the way for everything that followed. Their birth and death set off a chain reaction that shaped the universe into the vibrant, complex place we see today. And as we study the CMB, we are essentially reading the universe's history book, uncovering the story of these ancient stars and their lasting legacy. With the cosmic dawn now illuminated, we turn our gaze to the next chapter in this cosmic saga, the formation of the universe's first galaxies. How did these early structures emerge from the ashes of the first stars, and what role did they play in shaping the cosmos? Let's continue our journey through the mysteries of the CMB to find out. Now turning to the 21st mystery hidden within the cosmic microwave background, we delve into the birth of the universe's first galaxies. These ancient structures, born from the ashes of the first stars, mark a critical turning point in cosmic history. But how does the CMB, a snapshot of the universe's infancy, help us unravel the story of these early galaxies? Let's explore the clues it holds and the challenges scientists face in piecing together this cosmic puzzle. The first galaxies began to form a few 100 million years after the Big Bang, emerging from the dense clouds of gas and dust left behind by the first stars. These early galaxies were small and faint compared to the majestic spirals and ellipticals we see today, but they were the building blocks of the universe's large-scale structure. The CMB provides a unique lens through which we can study these primordial galaxies, offering insights into their formation and evolution. One of the key ways the CMB helps us understand the first galaxies is through its temperature fluctuations. These tiny variations in the CMB's temperature reflect the distribution of matter in the early universe, revealing the seeds from which galaxies grew. As gravity pulled matter together, these seeds grew into dense regions that eventually collapsed to form the first galaxies. By analyzing these fluctuations, scientists can trace the growth of cosmic structures over billions of years, mapping the journey from the first stars to the first galaxies. However, studying these ancient galaxies is no easy task. they are incredibly distant and faint, making them difficult to observe directly. Additionally, the light they emitted has been stretched and redshifted by the expansion of the universe, shifting it into wavelengths that are challenging to detect. This is where the CMB becomes invaluable. By studying the CMB's polarization patterns, scientists can infer the presence of these early galaxies and the impact they had on their surroundings. For example, the process of reionization driven by the first galaxies left a distinct imprint on the CMB's polarization, providing clues about when and how these galaxies formed. The birth of the first galaxies was a transformative event in cosmic history. These early structures not only illuminated the universe but also played a crucial role in shaping its evolution. As galaxies formed and grew, they began to cluster together, creating the vast cosmic web we see today. The CMB helps us trace this intricate web, revealing how the universe's first galaxies laid the foundation for the complex, interconnected cosmos we inhabit. With the story of the first galaxies now unfolding, we turn our attention to the next mystery, the universe's first supermassive black holes. How did these enigmatic objects form in the early universe, and what role did they play in shaping the cosmos? Let's continue our journey through the mysteries of the CMB to uncover the secrets of these ancient giants. Now turning to the 22nd mystery hidden within the cosmic microwave background, we venture into the enigmatic realm of the universe's first supermassive black holes. These colossal objects lurking at the hearts of early galaxies are among the most mysterious and powerful entities in the cosmos. But how did they form so quickly after the Big Bang, and what clues does the CMB hold about their origins? Let's unravel the secrets of these ancient giants and their role in shaping the universe. Supermassive black holes are millions to billions of times more massive than our Sun, and their presence in the early universe poses a profound puzzle. According to standard models, black holes form from the collapse of massive stars, but the first stars were not massive enough to create supermassive black holes directly. So how did these behemoths emerge so soon after the universe began? One leading theory suggests that they grew from smaller, seed black holes, which formed either from the collapse of the first stars or from the direct collapse of dense gas clouds in the early universe. Over time, these seeds grew by consuming gas, dust, and even other black holes, eventually becoming the supermassive black holes we observe today. The CMB provides a unique window into this process. While the CMB itself doesn't directly show black holes, it reveals the conditions of the early universe that allowed them to form. For instance, the temperature fluctuations in the CMB reflect the distribution of matter, including the dense regions where black holes could have taken root. Additionally, the CMB's polarization patterns carry imprints of the first black hole's influence on their surroundings. As these black holes grew, they emitted intense radiation and powerful jets of particles, heating the surrounding gas and altering the universe's structure. These effects left subtle marks on the CMB, offering clues about when and how supermassive black holes formed. But why are these early supermassive black holes so important? For one, they played a crucial role in shaping the galaxies that hosted them. The energy they released influenced star formation and the growth of galaxies, creating a feedback loop that shaped the cosmos. Moreover, studying these black holes helps us understand the extreme physics of gravity and spacetime, testing our theories in ways that no laboratory on Earth can replicate. Could the CMB even hint at the existence of primordial black holes formed in the chaotic moments after the Big Bang? If so, this would revolutionize our understanding of the universe's earliest moments. As we ponder the mysteries of the first supermassive black holes, we prepare to explore the next chapter in our cosmic journey, the universe's first large-scale structures. How do the seeds of galaxies and clusters grow into the intricate cosmic web we see today? Let's continue our exploration of the CMB to uncover the origins of the universe's grand design. Now turning to the 23rd mystery hidden within the cosmic microwave background, we delve into the origins of the universe's first large-scale structures. These structures, such as galaxy clusters and cosmic filaments, form the backbone of the cosmic web, the intricate network that defines the universe's architecture. But how did these colossal formations emerge from the primordial soup of the early universe, and what role does the CMB play in unraveling their story? Let's explore how the CMB acts as a cosmic blueprint, revealing the seeds of the universe's grand design. The CMB is like a snapshot of the universe just 380,000 years after the Big Bang, capturing the faint echoes of its infancy. Within this ancient light, scientists have discovered tiny temperature fluctuations, imprints of the universe's earliest density variations. These fluctuations, though minuscule, were the seeds from which the first cosmic structures grew. Imagine tossing a handful of pebbles into a still pond. The ripples that spread outward are like the density variations in the early universe. Over billions of years, gravity amplified these ripples, pulling matter together to form the first galaxies, clusters, and filaments. Galaxy clusters, the largest gravitationally bound structures in the universe, are like bustling cities in the cosmic web. They contain hundreds or even thousands of galaxies, bound together by dark matter and gas. Cosmic filaments, on the other hand, are the threads that connect these clusters, forming a vast, interconnected network. Together, these structures create the cosmic web, a tapestry of matter that spans the entire observable universe. The CMB helps scientists map this web by revealing the distribution of matter in the early universe. By studying the patterns in the CMB, researchers can trace how these initial density variations evolved into the structures we see today. But why are these large-scale structures so important? They hold the key to understanding the universe's evolution and composition. For instance, the distribution of galaxy clusters and filaments provides clues about the amount and behavior of dark matter, the invisible substance that makes up most of the universe's mass. Additionally, the growth of these structures is influenced by dark energy, the mysterious force driving the universe's accelerated expansion. By studying the CMB, scientists can test theories about how dark matter and dark energy shaped the cosmos over billions of years. The CMB also offers insights into the process of structure formation itself. For example, the way galaxies and clusters are distributed today reflects the initial conditions of the universe as captured by the CMB. This connection allows scientists to test their models of cosmic evolution, refining our understanding of how the universe grew from a hot, dense state to the complex web of structures we observe today. It's like using a time machine to peer into the universe's past and see how it transformed over eons. As we marvel at the intricate cosmic web, we prepare to explore the next mystery, the universe's first cosmic voids. These vast, empty regions stretching between filaments and clusters are as enigmatic as the structures themselves. What can the CMB tell us about these cosmic deserts, and how do they fit into the larger story of the universe's evolution? Let's continue our journey through the CMB to uncover the secrets of these mysterious voids. Now turning to the 24th mystery hidden within the cosmic microwave background, we venture into the enigmatic realm of cosmic voids. These vast, nearly empty regions of space, stretching between the filaments and clusters of the cosmic web, are as mysterious as they are immense. Imagine standing in the middle of a desert so vast that the nearest oasis is millions of light years away. That's the eerie emptiness of a cosmic void, a place where galaxies are few and far between, and the density of matter is a mere whisper compared to the bustling clusters and filaments nearby. But why do these voids exist, and what can they tell us about the universe's large-scale structure? The CMB provides a unique window into the origins of these cosmic voids. Just as it reveals the seeds of galaxy clusters and filaments, it also captures the faint imprints of the regions that would eventually become voids. In the early universe, these regions were slightly less dense than their surroundings. Over billions of years, gravity pulled matter away from these underdense areas, leaving behind vast, empty expanses. The CMB allows scientists to trace this process, showing how the initial density variations in the early universe evolved into the cosmic voids we observe today. But why are these voids so important? They are not just empty spaces, they are a crucial part of the cosmic web, shaping the distribution of matter on the largest scales. The presence of voids influences the motion of galaxies and clusters, as matter flows from these empty regions toward denser areas. This movement helps scientists map the universe's large-scale structure and understand the forces that govern it. For example, the size and distribution of voids provide clues about the amount of dark matter and dark energy in the universe. By studying voids, researchers can test theories about how these mysterious components shape the cosmos. Cosmic voids also offer a unique laboratory for studying the properties of space itself. Because voids contain so little matter, they are ideal places to observe the effects of dark energy, the force driving the universe's accelerated expansion. In these empty regions, the influence of dark energy is more pronounced, making voids a key area for testing our understanding of this enigmatic force. Additionally, the emptiness of voids allows light from distant objects to travel through them with minimal interference, providing a clearer view of the universe's distant past. As we contemplate the vast emptiness of cosmic voids, we prepare to explore the next mystery, the universe's first cosmic filaments. These thread-like structures connecting galaxy clusters and weaving the cosmic web are as fascinating as the voids themselves. What can the CMB tell us about the formation of these filaments, and how do they fit into the larger story of the universe's evolution? Let's continue our journey through the CMB to uncover the secrets of these intricate cosmic threads. Now turning to the 25th mystery hidden within the cosmic microwave background, we delve into the intricate world of cosmic filaments. These thread-like structures, stretching across the universe like the delicate strands of a spider's web, connect galaxies and clusters, forming the backbone of the cosmic web. Imagine the universe as a vast tapestry, with filaments acting as the threads that hold everything together. Without these filaments, the cosmic web would unravel, and the universe's large-scale structure would collapse into chaos. But how do these filaments form, and what role do they play in the grand story of the cosmos? The CMB provides a unique glimpse into the origins of these cosmic filaments. Just as it reveals the seeds of galaxy clusters and voids, it also captures the faint imprints of the regions that would eventually become filaments. In the early universe, these regions were slightly denser than their surroundings, creating a network of interconnected pathways. Over billions of years, gravity pulled matter along these pathways, forming the long, thin structures we observe today. The CMB allows scientists to trace this process, showing how the initial density variations in the early universe evolved into the cosmic filaments that weave the cosmic web. But why are these filaments so important? They are not just cosmic decorations, they are the highways along which matter flows, shaping the distribution of galaxies and clusters. Filaments act as bridges, connecting dense regions of the universe and guiding the movement of matter. This flow of matter helps scientists map the universe's large-scale structure and understand the forces that govern it. For example, the length and thickness of filaments provide clues about the amount of dark matter and dark energy in the universe. By studying filaments, researchers can test theories about how these mysterious components influence the cosmos. Cosmic filaments also offer a unique perspective on the universe's evolution. Because they connect galaxies and clusters, they provide a way to study the interactions between these structures. For instance, filaments can channel gas and dust into galaxies, fueling the formation of new stars. They can also act as conduits for energy, transferring heat and radiation across vast distances. By studying filaments, scientists can gain insights into the processes that drive the growth and evolution of galaxies. As we marvel at the intricate beauty of cosmic filaments, we prepare to explore the next mystery, the universe's first cosmic web. This vast network of filaments, voids, and clusters forms the largest structure in the universe, shaping everything from the distribution of galaxies to the flow of matter. What can the CMB tell us about the formation of this cosmic web, and how does it fit into the larger story of the universe's evolution? Let's continue our journey through the CMB to uncover the secrets of this awe-inspiring cosmic tapestry. Now turning to the 26th mystery hidden within the cosmic microwave background, we explore the formation of the cosmic web, the largest and most intricate structure in the universe. Picture the cosmos as a vast, interconnected network with galaxies and clusters linked by delicate filaments, forming a web that spans billions of light years. This cosmic web is not just a random arrangement of matter. It is the scaffolding upon which the universe is built, shaping everything from the distribution of galaxies to the flow of cosmic energy. But how did this colossal structure come to be, and what can the CMB tell us about its origins? The CMB provides a unique window into the early universe, capturing the faint imprints of the density variations that would eventually grow into the cosmic web. In the moments following the Big Bang, tiny fluctuations in the density of matter and energy began to ripple through the universe. These fluctuations, preserved in the CMB, served as the seeds for the formation of the cosmic web. Over billions of years, gravity amplified these variations, pulling matter into dense regions that would become galaxies and clusters while leaving behind vast, empty voids. The filaments of the cosmic web formed along the pathways where matter flowed, connecting these dense regions and creating the intricate network we observe today. But why is the cosmic web so crucial to our understanding of the universe? It is the blueprint of the cosmos, revealing how matter is distributed on the largest scales. By studying the cosmic web, scientists can trace the evolution of the universe from its earliest moments to the present day. The web's structure provides clues about the nature of dark matter and dark energy, the mysterious components that make up most of the universe. For example, the distribution of filaments and voids can help researchers measure the amount of dark matter in the universe, while the expansion of the web over time offers insights into the effects of dark energy. The cosmic web also plays a vital role in the evolution of galaxies. Filaments act as cosmic highways, channeling gas and dust into galaxies and fueling the formation of new stars. They also serve as conduits for energy, transferring heat and radiation across vast distances. By studying the cosmic web, scientists can gain a deeper understanding of the processes that drive the growth and evolution of galaxies, shedding light on the forces that shape the universe. As we marvel at the beauty and complexity of the cosmic web, we prepare to uncover the next mystery, the universe's first cosmic collisions. These dramatic events, from galaxy mergers to cluster collisions, have shaped the cosmos in profound ways. What can the CMB tell us about these ancient collisions, and how do they fit into the larger story of the universe's evolution? Let's continue our journey through the CMB to explore the secrets of these cosmic encounters. Now turning to the 27th mystery hidden within the cosmic microwave background, we delve into the universe's first cosmic collisions. These monumental events, from galaxy mergers to cluster collisions, are not just dramatic spectacles. They are fundamental to understanding how the cosmos evolved into the intricate structure we see today. But how do these ancient collisions leave their mark on the CMB, and what can they tell us about the universe's history? The CMB, often referred to as the universe's baby picture, captures the faint echoes of these early collisions. In the early universe, as galaxies and clusters began to form, they didn't exist in isolation. Instead, they were drawn together by gravity, leading to colossal collisions that reshaped the cosmos. These events released enormous amounts of energy, creating ripples in the fabric of space-time that left subtle imprints in the CMB. By studying these imprints, scientists can piece together the story of these ancient encounters, revealing how they influenced the distribution of matter and the formation of large-scale structures. But why are these collisions so important? They are the cosmic equivalent of a domino effect, setting off a chain reaction that shaped the universe. When galaxies collide, they trigger bursts of star formation, creating new stars and planets. These collisions also redistribute matter, feeding supermassive black holes and fueling the growth of galaxy clusters. Over time, these processes shape the universe into the complex web of galaxies, clusters, and filaments we observe today. Without these early collisions, the universe as we know it might look entirely different. The CMB also provides clues about the nature of dark matter, the invisible substance that makes up most of the universe's mass. During collisions, dark matter behaves differently from ordinary matter, creating distinct patterns in the CMB. By analyzing these patterns, scientists can learn more about the properties of dark matter and its role in shaping the cosmos. For example, the way dark matter clumps together during collisions can reveal how it interacts with gravity, offering insights into one of the universe's greatest mysteries. As we explore the significance of these cosmic collisions, we are left with a thought-provoking question. What would the universe look like if these early collisions had never occurred? Would galaxies have formed differently, or would the cosmic web have taken on a completely new shape? These questions remind us of the delicate balance of forces that shape the universe, and how even the smallest changes could have led to a vastly different cosmos. With the next phase of our journey in sight, we prepare to uncover the 28th mystery, the universe's first cosmic explosions. These cataclysmic events, from supernova to gamma-ray bursts, released unimaginable amounts of energy, shaping the cosmos in profound ways. What can the CMB tell us about these ancient explosions, and how do they fit into the larger story of the universe's evolution? Let's continue our exploration to uncover the secrets of these cosmic fireworks. Now turning to the 28th mystery hidden within the cosmic microwave background, we explore the universe's first cosmic explosions. These cataclysmic events, from supernova to gamma-ray bursts, were some of the most powerful phenomena in the early universe, releasing energy on a scale that is almost impossible to comprehend. But how do these ancient explosions leave their mark on the CMB, and what can they tell us about the universe's evolution? The CMB, often described as the universe's oldest light, carries faint imprints of these early explosions. In the early universe, the first stars were massive and short-lived, ending their lives in spectacular supernova. These explosions scattered heavy elements like carbon, oxygen, and iron across the cosmos, seeding the universe with the building blocks of planets, stars, and even life itself. The energy released by these supernovae also heated the surrounding gas, creating ripples in the cosmic fabric that left subtle traces in the CMB. By studying these traces, scientists can reconstruct the timeline of these ancient explosions and understand how they shaped the universe. Gamma-ray bursts, the most energetic explosions in the universe, also played a crucial role. These bursts, often caused by the collapse of massive stars or the collision of neutron stars, released more energy in a few seconds than our Sun will emit in its entire lifetime. The intense radiation from these events ionized the surrounding gas, leaving distinct patterns in the CMB. These patterns provide clues about the frequency and distribution of gamma-ray bursts in the early universe, helping scientists piece together the story of how the cosmos evolved. But why are these explosions so significant? They are the cosmic engines that drove the universe's transformation. Supernova and gamma-ray bursts not only enriched the universe with heavy elements, but also influenced the formation of galaxies and large-scale structures. The shockwaves from these explosions compressed gas clouds, triggering the birth of new stars and galaxies. Over billions of years, these processes shaped the universe into the intricate web of galaxies, clusters, and filaments we observe today. Without these early explosions, the universe might have remained a dark, featureless void. The CMB also provides insights into the nature of dark energy, the mysterious force driving the universe's accelerated expansion. The energy released by these early explosions influenced the distribution of matter, creating patterns in the CMB that help scientists measure the amount of dark energy in the universe. By studying these patterns, researchers can learn more about the properties of dark energy and its role in shaping the cosmos. As we reflect on the power of these cosmic explosions, we are left with a thought-provoking question. What would the universe look like if these early events had never occurred? Would galaxies have formed differently, or would the cosmic web have taken on a completely new shape? These questions remind us of the delicate balance of forces that shape the universe, and how even the smallest changes could have led to a vastly different cosmos. With the next phase of our journey in sight, we prepare to uncover the 29th mystery, the universe's first cosmic rays. These high-energy particles, traveling through space at nearly the speed of light, hold clues about some of the most extreme environments in the cosmos. What can the CMB tell us about these ancient particles, and how do they fit into the larger story of the universe's evolution? Let's continue our exploration to uncover the secrets of these cosmic messengers. Now turning to the 29th mystery, we delve into the enigmatic world of the universe's first cosmic rays. These high-energy particles, racing through space at nearly the speed of light, are among the most elusive and fascinating phenomena in the cosmos. But what exactly are cosmic rays, and how do they connect to the cosmic microwave background? The answer lies in the faint whispers of the early universe, preserved in the CMB like a cosmic time capsule. Cosmic rays are not rays in the traditional sense, but rather charged particles, such as protons and atomic nuclei, accelerated to incredible speeds by some of the most extreme environments in the universe. They originate from sources like supernova remnants, black holes, and even distant galaxies. When these particles collide with the Earth's atmosphere, they create cascades of secondary particles which scientists can detect. But the story of cosmic rays begins long before they reach us. It starts in the early universe, where the first cosmic rays were born. The CMB provides a unique window into this ancient era. While cosmic rays themselves do not directly imprint on the CMB, their interactions with the early universe's matter and radiation left subtle traces. For instance, the energy released by cosmic rays could have influenced the ionization of gas in the early universe, creating ripples in the CMB that scientists can study today. These ripples offer clues about the origins and distribution of cosmic rays, helping researchers piece together the puzzle of how these particles shaped the cosmos. But why are cosmic rays so mysterious? For one, their origins are often shrouded in uncertainty. While we know some sources, like supernova, can produce cosmic rays, the highest energy particles remain unexplained. These ultra-high-energy cosmic rays carry millions of times more energy than particles produced in human-made accelerators, yet their exact sources remain a mystery. Some theories suggest they come from active galactic nuclei or even exotic phenomena like cosmic strings, but definitive answers are still elusive. The discovery of the first cosmic rays would have profound implications for our understanding of cosmic evolution. These particles are like cosmic messengers, carrying information about the most violent and energetic events in the universe. By studying their traces in the CMB, scientists can learn about the conditions of the early universe, the formation of galaxies, and even the nature of dark matter. Cosmic rays may also hold clues about the universe's magnetic fields, which play a crucial role in shaping the cosmos. To make this concept more relatable, imagine cosmic rays as cosmic detectives. Just as detectives gather clues to solve a mystery, cosmic rays carry information about their origins and the environments they passed through. By decoding these clues, scientists can reconstruct the history of the universe, much like piecing together a cosmic crime scene. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic neutrinos. These ghostly particles, almost invisible and rarely interacting with matter, hold secrets about the earliest moments of the cosmos. What can the CMB reveal about these elusive particles, and how do they fit into the grand tapestry of the universe's evolution? Let's continue our journey to explore the hidden world of cosmic neutrinos. Now turning to the 30th mystery, we explore the universe's first cosmic neutrinos, ghostly particles that are among the most elusive and mysterious in the cosmos. These tiny, nearly massless particles are so faint that they can pass through entire planets without interacting with matter. But despite their elusive nature, neutrinos play a crucial role in the story of the universe's evolution. What can the cosmic microwave background tell us about these enigmatic particles, and why are they so important for understanding the cosmos? Neutrinos are often called the universe's ghost particles because they rarely interact with anything. They are produced in vast quantities during nuclear reactions, such as those in the cores of stars, during supernova explosions, and even in the early moments of the Big Bang. In fact, the universe is filled with a cosmic neutrino background, a relic from the first second after the Big Bang, much like the CMB is a relic from the first light. But while the CMB is a snapshot of the universe at 380,000 years old, the cosmic neutrino background captures an even earlier era, just 1 second after the universe's birth. The CMB provides indirect clues about these primordial neutrinos. Although neutrinos themselves do not leave a direct imprint on the CMB, their presence influenced the early universe in subtle ways. For example, neutrinos contributed to the overall density of the universe, affecting how matter clumped together to form the first galaxies and stars. Their energy also helped shape the temperature fluctuations we see in the CMB, leaving behind a faint but detectable signature. By studying these patterns, scientists can infer the properties of the first neutrinos and their role in cosmic evolution. But why are neutrinos so important? For one, they are a window into the earliest moments of the universe. Unlike photons, which were trapped in the hot plasma of the early universe until recombination, neutrinos could travel freely almost immediately after the Big Bang. This means they carry information about the universe's conditions in its first second, a time that is otherwise inaccessible to us. Neutrinos also provide clues about the fundamental forces and particles that governed the early universe, helping scientists test theories about physics beyond the standard model. To make this concept more relatable, imagine neutrinos as cosmic time travelers. Just as a time traveler from the distant past might bring stories of a forgotten era, neutrinos carry information about the universe's infancy. By decoding their subtle signals in the CMB, scientists can reconstruct the conditions of the early universe, much like piecing together an ancient puzzle. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic photons. These particles of light, emitted during the Era of Recombination, mark the moment when the universe became transparent. What can the CMB reveal about these ancient photons, and how do they help us understand the universe's first light? Let's continue our journey to explore the hidden world of cosmic photons. Now turning to the 31st mystery, we delve into the universe's first cosmic photons, the particles of light that emerged during the Era of Recombination. This pivotal moment, occurring roughly 380,000 years after the Big Bang, marked the universe's transition from an opaque, fiery plasma to a transparent, glowing gas. It was during this time that electrons and protons combined to form the first atoms, allowing light to travel freely for the first time. The photons released during this era are what we now observe as the cosmic microwave background, or CMB, making it the oldest light in the universe and a direct window into its infancy. These ancient photons are more than just remnants of the past, they are cosmic storytellers. Each photon carries a record of the conditions in the early universe, encoded in its temperature and polarization. By studying these patterns, scientists can reconstruct the universe's history, much like reading the pages of a cosmic diary. The CMB's temperature fluctuations, for example, reveal the seeds of structure that would later grow into galaxies, clusters, and the vast cosmic web we see today. Without these first photons, our understanding of the universe's evolution would be incomplete. But why are these photons so significant? For one, they provide a snapshot of the universe at a critical moment in its history. Before recombination, the universe was a dense, hot soup of particles and radiation, where light was constantly scattered and absorbed. Once recombination occurred, the universe became transparent and photons could travel unimpeded. This moment of clarity allowed the universe to cool and set the stage for the formation of the first stars and galaxies. The CMB is essentially a photograph of this transformative era, capturing the universe as it was just before the cosmic dawn. To put it in perspective, imagine the CMB as a time capsule. Just as a time capsule preserves artifacts from a specific moment in history, the CMB preserves the conditions of the early universe. By analyzing the light from this ancient era, scientists can test theories about the universe's origins, its composition, and even its ultimate fate. The CMB has already confirmed key predictions of the Big Bang theory, such as the universe's age and its flat geometry, and continues to provide insights into mysteries like dark matter and dark energy. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic particles. These fundamental building blocks of matter, such as quarks and gluons, played a crucial role in shaping the cosmos. What can the CMB reveal about these ancient particles, and how do they help us understand the universe's earliest moments? Let's continue our journey to explore the hidden world of cosmic particles. Now turning to the 32nd mystery, we explore the universe's first cosmic particles, the fundamental building blocks that laid the foundation for everything we see today. These particles, such as quarks and gluons, existed in the earliest moments of the universe, long before atoms, stars, or galaxies came into being. The cosmic microwave background, or CMB, holds subtle clues about these ancient particles, offering scientists a unique window into the universe's infancy. Quarks and gluons are the smallest known components of matter, and they played a crucial role in the universe's evolution. In the first moments after the Big Bang, the universe was so hot and dense that quarks and gluons roamed freely, unable to bind together. As the universe expanded and cooled, these particles combined to form protons and neutrons, the building blocks of atomic nuclei. This process, known as quark confinement, marked a critical step in the formation of matter as we know it. Without quarks and gluons, the universe would have remained a featureless sea of energy, devoid of structure or complexity. But how does the CMB help us understand these ancient particles? The answer lies in the faint imprints they left behind. The temperature fluctuations in the CMB reflect the density variations in the early universe, which were influenced by the behavior of quarks and gluons. By studying these patterns, scientists can infer the properties of these particles and the conditions under which they existed. For example, the CMB provides evidence for the existence of a quark-gluon plasma, a state of matter that existed only in the universe's earliest moments. This plasma was a chaotic, energetic soup of particles, and its transition into protons and neutrons was a pivotal event in cosmic history. To make this concept more relatable, imagine the early universe as a boiling pot of water. In the beginning, the water is so hot that it's just a chaotic mix of steam and bubbles, much like the quark-gluon plasma. As the pot cools, the steam condenses into droplets and the bubbles settle, forming a calm, clear liquid. In the same way, the cooling universe allowed quarks and gluons to combine and form the stable particles that would eventually give rise to atoms, stars, and galaxies. The CMB is like a photograph of this transition, capturing the moment when the universe began to take shape. The study of these first cosmic particles is not just an academic exercise, it's essential for understanding the universe's evolution. Quarks and gluons are the foundation of all matter, and their behavior in the early universe shaped the cosmos we see today. By decoding the clues hidden in the CMB, scientists can piece together the story of how the universe went from a hot, dense soup of particles to the vast, structured cosmos we inhabit. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic forces. These fundamental interactions, such as gravity and electromagnetism, govern the behavior of particles and shaped the universe's evolution. What can the CMB reveal about these ancient forces, and how do they help us understand the cosmos's earliest moments? Let's continue our journey to explore the hidden world of cosmic forces. Now turning to the 33rd mystery, we delve into the universe's first cosmic forces, the fundamental interactions that shaped the cosmos from its earliest moments. These forces, gravity, electromagnetism, and the strong and weak nuclear forces, governed the behavior of particles, dictated the formation of structures, and set the stage for the universe's evolution. The cosmic microwave background, or CMB, provides a unique window into these ancient forces, offering clues about how they influenced the universe's infancy. Gravity, the most familiar of these forces, played a pivotal role in shaping the cosmos. In the early universe, gravity acted on tiny density fluctuations imprinted in the CMB, pulling matter together to form the first stars, galaxies, and larger structures. Without gravity, the universe would have remained a uniform sea of particles, never coalescing into the intricate web of galaxies we see today. The CMB's temperature fluctuations reveal these early density variations, allowing scientists to trace the influence of gravity over billions of years. Electromagnetism, another fundamental force, was equally crucial. This force governs the interactions between charged particles, such as electrons and protons, and is responsible for the formation of atoms. After the era of recombination, when electrons combined with protons to form neutral atoms, electromagnetism allowed light to travel freely, creating the CMB we observe today. The patterns in the CMB reflect the interplay between gravity and electromagnetism, showing how these forces work together to shape the universe's structure. The strong and weak nuclear forces, though less familiar, were no less important. The strong force binds quarks together to form protons and neutrons, while the weak force governs processes like radioactive decay. In the early universe, these forces were responsible for the formation of the first atomic nuclei during nucleosynthesis, a process that created the universe's first elements, hydrogen and helium. The CMB provides evidence for this process, as the abundance of these elements matches predictions based on the behavior of these forces. But why are these forces so significant for understanding the cosmos? Imagine the universe as a grand symphony, with each force playing a distinct instrument. Gravity sets the tempo, pulling matter together to form structures. Electromagnetism adds harmony, enabling the formation of atoms and the propagation of light. The nuclear forces provide the rhythm, driving the processes that created the building blocks of matter. Together, these forces orchestrated the universe's evolution, transforming a hot, dense soup of particles into the vast, structured cosmos we inhabit today. The CMB allows scientists to study these forces in action, offering a snapshot of the universe just 380,000 years after the Big Bang. By analyzing the temperature fluctuations and polarization patterns in the CMB, researchers can test theories about the behavior of these forces and refine our understanding of cosmic evolution. For example, the CMB provides evidence for the existence of dark energy, a mysterious force driving the universe's accelerated expansion. This discovery has profound implications for our understanding of gravity and the ultimate fate of the cosmos. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic fields. These invisible structures, such as the Higgs field, played a crucial role in shaping the universe's evolution. What can the CMB reveal about these ancient fields, and how do they help us understand the cosmos's earliest moments? Let's continue our journey to explore the hidden world of cosmic fields. Now turning to the 34th mystery, we explore the universe's first cosmic fields, invisible structures that permeate space and time, shaping the very fabric of reality. Among these fields, the Higgs field stands out as one of the most significant. It is the field responsible for giving particles their mass, a process that occurred just moments after the Big Bang. Without the Higgs field, particles would zip through the universe at the speed of light, never forming the atoms, stars, or galaxies we see today. The cosmic microwave background, or CMB, offers a unique glimpse into these ancient fields, providing clues about how they influenced the universe's earliest moments. The Higgs field is not the only cosmic field that played a role in shaping the cosmos. Other fields, such as the inflaton field, are thought to have driven the rapid expansion of the universe during cosmic inflation. This period of exponential growth, which occurred in the first fraction of a second after the Big Bang, left its imprint on the CMB. The tiny temperature fluctuations we observe in the CMB are believed to be the result of quantum fluctuations in these fields, stretched across the universe by inflation. These fluctuations served as the seeds for the formation of galaxies, clusters, and other large-scale structures. But why are these fields so important for understanding the cosmos? Imagine the universe as a vast, interconnected network of energy and matter. Cosmic fields are the threads that weave this network together, governing the behavior of particles and the evolution of the universe. The Higgs field, for example, not only gives particles mass but also determines the strength of their interactions. Without it, the universe would lack the complexity and diversity we see today. Similarly, the inflaton field set the stage for the universe's expansion, creating the conditions necessary for the formation of structures. The CMB allows scientists to study these fields in action, offering a snapshot of the universe just 380,000 years after the Big Bang. By analyzing the temperature fluctuations and polarization patterns in the CMB, researchers can test theories about the behavior of these fields and refine our understanding of cosmic evolution. For example, the CMB provides evidence for the existence of dark energy, a mysterious field that is driving the universe's accelerated expansion. This discovery has profound implications for our understanding of cosmic fields and the ultimate fate of the cosmos. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic symmetries. These fundamental principles, which govern the behavior of particles and forces in the early universe, played a crucial role in shaping the cosmos. What can the CMB reveal about these ancient symmetries, and how do they help us understand the universe's earliest moments? Let's continue our journey to explore the hidden world of cosmic symmetries. Now turning to the 35th mystery, we delve into the universe's first cosmic symmetries, fundamental principles that govern the behavior of particles and forces in the early universe. These symmetries are like the invisible rules of a cosmic game, dictating how matter, energy, and forces interact. One of the most intriguing symmetries is the balance between matter and antimatter. In the early universe, these two were created in equal amounts, yet today we live in a universe dominated by matter. Why this imbalance exists is one of the greatest puzzles in cosmology, and the cosmic microwave background, or CMB, holds vital clues to unraveling this mystery. The CMB provides a snapshot of the universe just 380,000 years after the Big Bang, capturing the remnants of these ancient symmetries. By studying the temperature fluctuations and polarization patterns in the CMB, scientists can test theories about how these symmetries shape the cosmos. For example, the near-perfect uniformity of the CMB suggests that the early universe was highly symmetric, with matter and antimatter distributed evenly. However, something must have broken this symmetry, leading to the dominance of matter over antimatter. This process, known as baryogenesis, is thought to have occurred in the first moments after the Big Bang, and the CMB offers a unique window into this critical period. To understand why these symmetries are so important, imagine the universe as a perfectly balanced scale. In the beginning, matter and antimatter were equal on both sides, but as the universe evolved, the scale tipped in favor of matter. This imbalance allowed galaxies, stars, and planets to form, creating the rich and diverse cosmos we see today. Without this asymmetry, matter and antimatter would have annihilated each other, leaving behind a universe filled with nothing but energy. The CMB helps scientists piece together how and why this symmetry was broken, offering insights into the fundamental laws of physics. One of the most compelling theories to explain this asymmetry involves a phenomenon called charge parity violation, or CP violation. This process, which occurs in certain particle interactions, could have tipped the scales in favor of matter. The CMB provides evidence for CP violation by revealing subtle patterns in the polarization of light, which may be linked to the behavior of particles in the early universe. These findings not only shed light on the origins of matter, but also help scientists refine their understanding of the fundamental forces that govern the cosmos. As we prepare to explore the next mystery, we turn our attention to the universe's first cosmic asymmetries. These imbalances, which emerged from the breaking of symmetries, played a crucial role in shaping the cosmos. What can the CMB reveal about these asymmetries, and how do they help us understand the universe's evolution? Let's continue our journey to uncover the hidden forces that shape the cosmos. Now turning to the 36th mystery, we explore the universe's first cosmic asymmetries, the imbalances that emerged from the breaking of the early symmetries we just discussed. These asymmetries are not just quirks of nature, they are the very reason our universe exists as we know it. Without them, the cosmos would be a very different place, perhaps even devoid of the galaxies, stars, and planets that make up our home. The cosmic microwave background, or CMB, holds vital clues about how these asymmetries arose and why they are so crucial to understanding the universe's evolution. One of the most profound asymmetries is the imbalance between matter and antimatter. In the early universe, matter and antimatter were created in equal amounts, yet today we live in a universe dominated by matter. This imbalance is one of the greatest mysteries in cosmology. If matter and antimatter had remained perfectly balanced, they would have annihilated each other, leaving behind a universe filled with nothing but energy. So, what caused this asymmetry? The CMB provides a unique window into this critical question. By studying the temperature fluctuations and polarization patterns in the CMB, scientists can test theories about how this imbalance came to be. One leading theory involves a process called baryogenesis, which occurred in the first moments after the Big Bang. During this period, a slight asymmetry in the behavior of particles and antiparticles could have tipped the scales in favor of matter. The CMB offers evidence for this process by revealing subtle patterns in the polarization of light, which may be linked to the behavior of particles in the early universe. These patterns are like cosmic fingerprints, preserving the traces of the universe's first asymmetries. By decoding these fingerprints, scientists can piece together the story of how matter came to dominate the cosmos. But why are these asymmetries so important? Imagine the universe as a vast, intricate tapestry. The symmetries are the threads that hold it together, but the asymmetries are the patterns that give it meaning. Without the imbalance between matter and antimatter, the tapestry would be blank, no stars, no galaxies, no life. the CMB helps us understand how these patterns emerged, offering insights into the fundamental laws of physics that govern the universe. It's like having a time machine that allows us to peer back into the earliest moments of cosmic history and witness the birth of the structures we see today. As we prepare to explore the next mystery, we turn our attention to the universe's first cosmic transitions. These pivotal moments, marked by dramatic changes in the state of the universe, played a crucial role in shaping the cosmos. What can the CMB reveal about these transitions, and how do they help us understand the universe's evolution? Let's continue our journey to uncover the hidden forces that shape the cosmos. Now turning to the 37th mystery, we delve into the universe's first cosmic transitions, moments of profound change that reshape the cosmos in its infancy. These transitions are like cosmic turning points, marking the moments when the universe shifted from one state to another, setting the stage for everything that followed. The cosmic microwave background, or CMB, serves as a time capsule, preserving the echoes of these dramatic events and offering scientists a way to study them in extraordinary detail. One of the most significant transitions occurred at the end of cosmic inflation, a period of rapid expansion that took place just fractions of a second after the Big Bang. During inflation, the universe expanded exponentially, smoothing out irregularities and laying the groundwork for the large-scale structure we see today. But inflation couldn't last forever. When it ended, the universe underwent a phase transition, releasing an enormous amount of energy and giving rise to the hot, dense plasma that filled the early cosmos. This transition is often compared to water freezing into ice, a sudden and dramatic change in state that fundamentally altered the universe's properties. The CMB provides crucial evidence for this transition. Tiny temperature fluctuations in the CMB reflect the density variations that emerged as inflation ended. These fluctuations are like ripples on the surface of a pond, preserving the imprint of the universe's first moments. By studying these patterns, scientists can test theories about how inflation ended and how the universe transitioned into the next phase of its evolution. It's like having a snapshot of the universe at the precise moment it began to take shape. But why are these transitions so important? They represent the moments when the universe's fundamental forces and particles began to behave differently, setting the stage for the formation of matter, galaxies, and stars. Without these transitions, the universe would have remained a featureless sea of energy, devoid of the structures that make it so rich and complex. The CMB allows us to trace these changes, offering insights into the physics that governed the early universe and the processes that shaped its evolution. As we prepare to explore the next mystery, we turn our attention to the universe's first cosmic instabilities. These instabilities, born from the seeds of the early universe, played a crucial role in the formation of galaxies and other large-scale structures. What can the CMB reveal about these instabilities, and how do they help us understand the universe's evolution? Let's continue our journey to uncover the hidden forces that shape the cosmos. Now turning to the 38th mystery, we explore the universe's first cosmic instabilities, the subtle yet powerful forces that set the stage for the formation of galaxies and other large-scale structures. These instabilities are like the first cracks in a frozen lake, small at first but destined to grow and reshape the entire surface. The cosmic microwave background, or CMB, holds the key to understanding these early disturbances, offering a glimpse into the moments when the universe began to shift from a smooth, uniform state to one filled with complexity and structure. Gravitational instabilities played a central role in this transformation. In the early universe, tiny fluctuations in density, imprinted during the era of inflation, began to grow under the influence of gravity. Imagine a calm ocean where small ripples gradually build into towering waves. Similarly, these density variations, though initially minuscule, grew over time, pulling matter together and creating the seeds for galaxies, clusters, and the vast cosmic web we observe today. The CMB captures these early ripples, preserving them as temperature fluctuations that scientists can study to understand how the universe evolved from a nearly featureless expanse to the intricate tapestry we see now. But why are these instabilities so crucial? They represent the first steps in the universe's journey toward complexity. Without them, matter would have remained evenly distributed, and the cosmos would have lacked the structures necessary for stars, planets, and life itself. The CMB allows us to trace the origins of these instabilities, providing a window into the processes that shaped the universe's large-scale structure. By analyzing the patterns in the CMB, scientists can test theories about how gravity amplified these early fluctuations and how they eventually led to the formation of galaxies and clusters. To make this concept more relatable, think of the universe as a vast cosmic dough. In its early stages, the dough was smooth and uniform, but as it expanded and cooled, small lumps and bumps began to form. These imperfections grew over time, eventually giving rise to the rich, textured bread we see today. The CMB is like a photograph of the dough at a critical moment, capturing the early stages of this transformation and allowing us to study how the universe's first instabilities set the stage for everything that followed. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic fluctuations. These fluctuations, the tiny variations in density and temperature that seeded the formation of galaxies, are the building blocks of the cosmos. What can the CMB reveal about these fluctuations, and how do they help us understand the universe's evolution? Let's continue our journey to uncover the hidden forces that shape the cosmos. Now turning to the 39th mystery, we delve into the universe's first cosmic fluctuations, the tiny ripples in density and temperature that laid the foundation for everything we see in the cosmos today. These fluctuations, imprinted in the cosmic microwave background, or CMB, are like the faintest whispers of the early universe, carrying secrets about how galaxies, stars, and even life itself came to be. But what exactly are these fluctuations, and why do they hold such profound significance for our understanding of the universe? Imagine the early universe as a vast, calm sea. At first glance, it appears smooth and uniform, but beneath the surface, tiny waves begin to form. These waves are the cosmic fluctuations, small variations in density and temperature that emerged during the universe's infancy. The CMB captures these fluctuations as subtle differences in temperature, creating a map of the universe's earliest moments. By studying this map, scientists can trace how these tiny ripples grew over billions of years, eventually giving rise to the galaxies and clusters that fill the cosmos. But why are these fluctuations so important? They are the seeds of structure in the universe. Without them, matter would have remained evenly distributed, and the cosmos would have been a featureless void. Instead, these fluctuations acted as the starting points for gravity to work its magic, pulling matter together and forming the first clumps of gas and dust. Over time, these clumps grew larger, collapsing under their own gravity to form stars, galaxies, and the intricate cosmic web we observe today. The CMB allows us to see these seeds in their earliest form, providing a snapshot of the universe just moments after the Big Bang. To put it simply, these fluctuations are the universe's blueprint. They tell us how matter was distributed in the early cosmos and how gravity shaped that matter into the structures we see today. By analyzing the patterns in the CMB, scientists can test theories about the universe's origins and evolution, answering questions like, what caused these fluctuations in the first place? How did they grow over time, and what do they reveal about the fundamental laws of physics? As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic patterns. These patterns, the intricate designs woven into the fabric of the CMB, are more than just beautiful. They are the fingerprints of the cosmos, revealing the forces that shaped the universe from its earliest moments. What can these patterns tell us about the universe's evolution, and how do they connect to the larger story of the cosmos? let's continue our journey to uncover the hidden artistry of the universe. Now turning to the 40th mystery, we explore the universe's first cosmic patterns, the intricate designs etched into the fabric of the cosmic microwave background, or CMB. These patterns, formed by temperature fluctuations in the early universe, are more than just random variations. They are the fingerprints of the cosmos, revealing the forces that shaped the universe from its earliest moments. Imagine the CMB as a vast cosmic tapestry, woven with threads of light and shadow, each thread representing a fluctuation in temperature and density. These fluctuations, though tiny, hold the key to understanding how the universe evolved from a hot, dense soup of particles into the complex web of galaxies and clusters we see today. The patterns in the CMB are like a cosmic code, a language written in the language of temperature and density. By decoding this language, scientists can uncover the secrets of the universe's origins. For instance, the distribution of these fluctuations tells us about the initial conditions of the universe, the balance of matter and energy, and the forces that governed its expansion. The most striking feature of these patterns is their scale. Some fluctuations are small, representing tiny ripples in the early universe, while others are larger, corresponding to vast cosmic structures. Together, they form a harmonious design, a symphony of creation that echoes through the ages. But why are these patterns so important? They are the blueprint of the universe's structure. Just as the grain of wood determines the strength and beauty of a piece of furniture, these patterns determined how matter would clump together and form galaxies, stars, and planets. Without these patterns, the universe would have remained a featureless void, a sea of uniform energy with no structure or form. Instead, the patterns acted as the seeds of creation, guiding the growth of cosmic structures over billions of years. By studying these patterns, scientists can trace the evolution of the universe, from its fiery birth to the intricate cosmic web we observe today. The beauty of these patterns lies not only in their scientific significance but also in their aesthetic appeal. The CMB is a masterpiece of cosmic art, a canvas painted with the brushstrokes of the early universe. Each fluctuation is a stroke of genius, a testament to the creativity of the cosmos. As we gaze at the CMB, we are not just looking at a map of the universe, we are witnessing the birth of beauty itself, the moment when chaos gave way to order and the universe began to take shape. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic rhythms. These rhythms, the oscillations of sound waves in the early universe, are the heartbeat of creation, the pulse that set the universe in motion. What can these rhythms tell us about the universe's evolution, and how do they connect to the larger story of the cosmos? Let's continue our journey to uncover the hidden symphony of the universe. Now turning to the 41st mystery, we delve into the universe's first cosmic rhythms, the oscillations of sound waves that rippled through the early universe. These rhythms, captured in the cosmic microwave background, or CMB, are like the heartbeat of creation, a pulse that set the universe in motion. Just as the steady beat of a drum can guide a song, these cosmic rhythms guided the formation of the universe's first structures, shaping the cosmos into the intricate web we see today. Imagine the early universe as a vast, hot plasma, a dense soup of particles and energy. Within this plasma, sound waves traveled like ripples on a pond, creating areas of higher and lower density. These waves, known as baryon acoustic oscillations, left their mark on the CMB, imprinting a pattern of peaks and troughs that scientists can still observe today. These patterns are not random, they are the echoes of the universe's first rhythms, a cosmic symphony that played out in the moments after the Big Bang. Why are these rhythms so important? They provide a cosmic ruler, a way for scientists to measure distances in the universe. The spacing between the peaks in the CMB corresponds to the distance sound waves could travel before the universe cooled enough for light to escape. By studying these patterns, scientists can map the universe's expansion and understand how it has evolved over billions of years. these rhythms also reveal the balance of forces in the early universe, the interplay between gravity pulling matter together and radiation pushing it apart. Without these oscillations, the universe might have remained a featureless void, a sea of uniform energy with no structure or form. To make this concept more relatable, think of the universe as a giant musical instrument. The sound waves in the early universe were like the vibrations of a guitar string, creating harmonics that shaped the cosmos. Just as a musician can tune an instrument to create beautiful music, the universe's first rhythms tuned the cosmos, setting the stage for the formation of galaxies, stars, and planets. These rhythms are the foundation of the cosmic web, the intricate network of filaments and voids that make up the universe's large-scale structure. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic harmonies. These harmonies, the balance between different forces and particles, are the key to understanding how the universe evolved from a chaotic soup of energy into the ordered cosmos we see today. What can these harmonies tell us about the universe's origins, and how do they connect to the larger story of creation? Let's continue our journey to uncover the hidden symphony of the universe. Now turning to the 42nd mystery, we explore the universe's first cosmic harmonies, the delicate balance between forces and particles that shaped the cosmos in its earliest moments. These harmonies, imprinted in the cosmic microwave background, or CMB, are like the perfect tuning of a grand orchestra, where every note aligns to create a symphony of creation. Without this balance, the universe as we know it might never have existed. Imagine the early universe as a stage where gravity, radiation, and matter all played their parts. Gravity pulled matter together while radiation pushed it apart, creating a cosmic tug-of-war. The CMB captures the echoes of this interplay, revealing how these forces harmonize to create the conditions for galaxies, stars, and planets to form. This balance was not accidental. It was a precise calibration that allowed the universe to evolve from a chaotic soup of energy into the structured cosmos we see today. Why are these harmonies so crucial? They reveal the fundamental laws that govern the universe. For instance, the balance between matter and radiation in the early universe determined how quickly structures could form. If radiation had dominated, matter might have been too dispersed to clump together. If gravity had been too strong, the universe might have collapsed back on itself. The CMB shows us that these forces were perfectly tuned, allowing the universe to expand and cool at just the right rate. To make this concept more relatable, think of the universe as a finely tuned instrument. Just as a musician adjusts the tension on a guitar string to produce the perfect pitch, the universe's first harmonies adjusted the balance of forces to create the conditions for life. These harmonies are the foundation of the cosmic web, the intricate network of galaxies and voids that make up the universe's large-scale structure. Without them, the universe might have remained a featureless void, a sea of uniform energy with no structure or form. What can these harmonies tell us about the universe's origins? They hint at the existence of deeper laws, perhaps even a grand cosmic design. Could the universe's perfect balance be the result of chance, or is there something more profound at work? These questions challenge our understanding of reality and invite us to explore the mysteries of existence. As we prepare to uncover the next mystery, we turn our attention to the universe's first cosmic dissonances. These dissonances, the moments when the balance was disrupted, are the key to understanding how the universe evolved from a harmonious beginning into the complex cosmos we see today. What can these disruptions tell us about the universe's history, and how do they connect to the larger story of creation? Let's continue our journey to uncover the hidden